Welcome to Electric Power System Fundamentals. This is an introduction course. It's a course that sets a foundation for anyone that wants to get into the electric power industry. It's a great course. It covers many different areas. We're going to get into all aspects of electric power systems. We're going to start out with some fundamentals and some concepts. We're going to go into some basic electronics. And we're going to move into three-phase power, and then go into the big bulk power system equipment, how it all operates, how you control it, the issues about system reliability and coordination, protection, safety. We're going to get into all aspects of electric power systems in this one course. So it's a high-level course. We'll drill down into some detail when it comes to some of the things that you really need to have a fundamental understanding of. But a lot of the areas that we're going to cover later in future modules, we're just going to give a high-level mention of them. For example, we talk about substation equipment. We're just going to introduce transformers and circuit breakers and those types of things. But in some of the other courses, you're going to learn a whole lot more about how they work, how they operate, how they affect system reliability, and all those kinds of great things. So this is just a good introductory course. It'll help you in all aspects of the electric power system. Okay, we're going to go on to slide number 2. And the learning outcomes here, we're going to be talking about how this course is going to deal with generation, transmission, distribution. We're going to get into consumption, metering, those types of things, system control, SCADA systems. And of course, we're going to talk about safety, electrical safety. So we're going to hit some of those items when we're finished with this course. Another major outcome of this course is we're going to explain how all of the electrical terms and the equipment and operations and the complexities of all of this, we're going to keep it to simple to understand terminology. We're going to try to keep it real basic, maybe too basic, but that's okay. We want to get everybody on the same page as we go forward. Okay, we want to be able to, when you leave, that you feel confident going into meetings or talking to other people in the industry so that you can communicate well and understand what they're saying and ask the right kinds of questions. We want to get every student knowledgeable enough and familiar and confident enough to know what they need to know about the basic bulk power electric grid system that we have today. Okay, so the first chapter we're going to get into is terminology and concepts, and we're going to discuss the basic ones that are used in the electric power system, so you're going to be able to understand them and apply them yourselves. We're going to talk about how DC circuits work. What's the difference between DC and AC, and what makes up direct current DC circuits, and talk about some of the fundamental laws like Ohm's law and Kirchhoff's law. And what's interesting, when you learn some of these laws, they all apply to the very large bulk power systems. When we talk about substations and power coming in and out of a substation, it all has to add up to zero. What comes in and what goes out, and what's consumed, all has to add up to zero. Well, that's basically Kirchhoff's law, but we're going to learn that law at its fundamental levels, and that's down when we talk about DC current and voltage. So some of these laws and things that we pick up here in this introduction module really applies in the bulk power system. It's kind of interesting. The only thing that's different is the magnitude of the numbers. The concepts are the same. So just, sit back, relax, get a good feel for the fundamentals, because that's going to help you through the rest of your career. And that's what this class is focused on. Okay, so we're going to talk about more fundamentals. We're going to talk about some of the components, simple components. Talk about magnetism and phase angles and some of the basic math concepts that enter into this, what power factor is, and Faraday's law. All this might be new to you, but you'll see it all makes common sense. Part of the objective of this course is to make sure that all these are explained in simple to understand terms, and that's the goal here. Then we're going to get into three-phase power. We're going to take these basic concepts of DC and AC and all these different rules and laws and apply to three-phase power. Our bulk electric power system in the world is based on three-phase power. Why and why we do it, how it works, and all those reasons, we're going to get familiarized with all those concepts. So, you know, the end of this section is going to be building a three-phase power system in your mind and getting all the concepts understood so we can move on to bigger and better things. Okay, once you kind of have all that understood, then we're going to take you through the simulator. And you're going to learn how to operate a power system simulator. And this simulator is going to be used throughout all these modules to reinforce and to get you familiar with how the real power system works. Fortunately, you will not be tripping anybody's power off. You will just be seeing red and green circuit breakers tripping and voltage collapse and frequencies shifting and crazy things like that. But this particular, this first course is going to get you familiar with operating the power system simulator. I think you'll enjoy that. Okay, so the first module we're going to get into here on the on terminology has to do with the concepts. We're going to you're going to understand the four fundamental terms that are used in power systems and really be able to differentiate between voltage, current, power, and energy. And it's amazing how people mix up energy and power. They don't really know the difference. Well, let's really know the difference after we get done with this course so you can understand the concepts, okay? We're going to talk about the different voltage terms. I mean, in voltage, there's several different ways to describe what voltage is. So once we understand voltage, we're going to talk about DC, AC, RMS, peak, symmetrical, asymmetrical. We're going to get into all those different types of voltages in our terms here. Get to know those fundamentals. Then we're going to apply them to high voltage conditions. You know, what is in a bulk power system? What are the basic voltage levels and those types of things? So we got a lot to cover here in just basic terminology, but that's going to set a foundation for our communications. Okay. Now, we want you to be able to communicate with management. We want you to be able to communicate with other vendors or maybe manufacturers or customers, depending on what your job is or what you want your career to be. And this is going to set the foundation for learning. All right, so the very first one that we're going to cover today is voltage. Now, voltage is a push. It's a force. It does nothing by itself. It has potential to do work. It appears between 2 points. It's always there. You know, and it's voltage. Voltage is a potential energy. Sometimes it's called potential. And what that means is if I take this remote, for example, and I put it on my hand, it has no energy, no potential energy. It's at rest. If I lift this remote up an elevation or a height, it now has potential energy. If I let it go, it's going to fall. It's going to convert into kinetic energy. But the fact that it has potential energy at this point means it is ready to perform some work for us. Voltage is the same way. Instead of measuring it in 12 inches, we're going to measure it in 12 volts. Okay, so voltage is potential energy. It has the ability to produce work, do things for us, but it does nothing by itself. It's like pressure in a water pipe. Okay, the next one is current. Now, current is what flows. It's the electrons moving in a conductor. Okay, and conductors are materials that have electrons that are available to move. They're not held tight to their nucleus. They're actually valence, outer bound electrons that are pretty easy to push from atom to atom and actually get them to move with another charge. And we'll get into that a little bit more. So when we talk about current, we're talking about the flow of electrons in a wire. And current happens to be 628 times 10 to the 16th power. That's the number 628. You can see at the bottom of that slide. With 16 zeros after it, that's how many electrons flowing through a point equals 1 amp. So 1 amp has that many electrons moving. So electrons are extremely small, and we'll get to know that. Now, in a circuit, the electrons that are flowing in the circuit must come back to the source. They start from the source, and they return to the source. And based on what conditions they go through in that circuit will determine how much current is flowing. If there's resistance in the circuit, fewer electrons are going to flow, reducing the current, etc. We're going to get into those types of things as we go. Now, one of the things about current is when the electrons are flowing through a conductor, there's resistance in that conductor, kind of like friction, and that produces heat. So when electrons are flowing through resistance, they produce heat. That's like in an electric stove, and the burners on the top are getting red hot. That's current flowing through resistance producing heat. Or a toaster. Okay, so we're talking about current produces the heat through the resistance of the conductors. Okay, now one of the fundamentals about current is when current flows through a wire, it produces a magnetic field. Okay, when current flows through a wire, it produces a magnetic field. And I'll show you a slide on that. Now, one thing I'd like to back up on just a bit is voltage. You could produce voltage when you have a conductor experiencing a changing magnetic field. In other words, if you take a conductor or a coil of wire and expose it to a changing magnetic field, like the north and south poles are moving, you will produce voltage in the conductor. So we have a couple of physical laws I'm talking about. Faraday's law, which we're going to talk about more with voltage, producing a voltage with a changing magnetic field, and then here you have current. When current is flowing in a wire, you have a physical law that when current flows through a wire, it produces a magnetic field. So with current, you produce magnetic fields. With voltage, changing magnetic fields can produce a voltage on a conductor. So those are some of the things. We're going to get more into it, but I want to kind of give you a little foundation of where we're heading after we go through here. So here is a slide on current. Now, as you can see, there's a voltage source. There's a negative sign up on the top, positive sign on the bottom, and the current is actually flowing through the load and back into the source. So when you see a negative sign here, and these are electrons in a conductor flowing through a load and coming back, depending on the resistance or the characteristics of the load will determine how many electrons are actually flowing. So that's what current is. Current is the flow of electrons. Okay? Now, I don't know why it is, but we have two methods of determining the direction of current. One of them is called electron flow notation, and that is where you have a battery and the electrons are actually coming out of the negative side of the battery and flowing into the load and coming out of the load and going into the positive side of the battery. That is, electrons flow. Makes sense. The electrons coming out of the negative side of a battery, going through a load and coming into the positive side, and then that source kicks them out again and pushes them out the negative side, and we go around in circles like that. That is called electron flow. Then we have what's called conventional flow. Okay, now it's sometimes called hole flow. And in this case, we think of the positive as being the source of current, and the current goes through the load and comes into the negative. A lot of times we think of positive current flow as is conventional current flow, but in reality, physically, we think of the electrons flowing. When the electrons are flowing, they're actually leaving holes in their atoms. So the electron goes from one atom to the next atom to the next atom. It's actually leaving a space or a hole when it left and went to the other one. Here's a space over here. Okay? And when this electron comes and takes over that space, it left a hole this way. So the holes are going this way, The electrons are going this way, so which way is positive? Which way is current flow? Well, there's two conventions. There's the electron flow and conventional. When you look at schematics, transistors, diodes, all those types of things, the arrows show the direction of the positive or conventional current flow. It's actually the direction of the holes that are flowing. So when you see schematics and you see these holes or you see arrows, that's considered positive or conventional current flow. I know it's a little confusing, but at the end of the day, it doesn't really matter. At the end of the day, it just means that you have current, you have voltage. Exactly which way the current is flowing, is not a big thing. It's just, I just want to point out that there are two conventions. All right. So we're going to be using positive DC current flow, which is used in the electronics industry and the telecommunications industry, and not so much in the power industry. We're going to be dealing with that, looking at it a little bit differently. Now, when it comes to power and energy, those terms, okay, power is measured in watts and energy is measured in watt hours. When we talk about a toaster that is 1,200 watts, for example, or a light bulb that is 100 watts, that's how much power it consumes, okay, to produce the work that we're expecting. Now, energy says that device or that component is absorbing or consuming that much power over a period of time. So if we had a 100-watt light bulb running for 10 hours, that would be 100 times 10 or 1,000 watt hours or 1 kilowatt hour. Okay, so when we think of energy, you got to think of with time involved. If a generator at a big power plant is putting out, 200 megawatts of power, is it doing it every hour? What is the time associated with it? Because if it was 1 hour it was producing, the energy out of that generator would be 200 megawatt hours. If that 200 megawatt generator were producing power for 2 hours, then it would be 400 megawatt hours, yet it's a 200 watt generator. See the difference between power and energy. Power is the rating of the device. Energy associates it with time. So when we go to the side of our house and we look at our kilowatt hour meters, kilowatt hours means in that month or that billing cycle that the loads and the appliances, what have you in a house, totaled up to be so many kilowatt hours. So that's energy. So think in terms of energy or power. And once you understand that the one is associated with time, hopefully there'll be less confusion. Okay, now let's talk about DC voltage and current. Now here's a graph that shows voltage here on the side versus time. And the voltage is constant. This would represent like a battery. A battery is constant voltage. And maybe when a battery wears out, it drops down in voltage, but the voltage here is constant. That's the key. When we look at AC, or alternating current, that's when the voltage and current are alternating positive and negative with respect to time. Here we have the voltage going positive for a peak positive, going through 0 voltage, and negative for a peak negative back to 0 again. And in AC, we typically go alternating so many complete cycles every second, which is referred to as frequency. And in a bulk electric power system, we are very concerned about frequency stability, frequency being 60 hertz or 60 cycles per second in the U.S., in most of North America. And then we have in Europe and parts of South America and even parts of Mexico, we have 50 cycle per second or 50 hertz. So typically in our world, we have 60 and 50 hertz electric power systems. But that has to do with AC, and there's good reasons why we use AC in power versus DC. We could go all the way back to Tom Edison versus Westinghouse, but we're not going to go back to that much history right now. Thomas Edison, of course, is DC, and Westinghouse is AC. And whatever happened with all that, that could be a whole other course. It's actually interesting reading in history, and it has a lot to do with where we are today. But anyway, AC and DC, those are our two. Now, we're going to start talking about AC a little bit more specifically. In AC voltage, we have the peak voltage, and we have the peak negative voltage, and we have what's referred to as the root mean squared. Now, this we deal with root mean squared because we have an issue that if you take the average value of voltage, it becomes 0. So the average value of voltage in an AC signal is 0. And we know it has potential to do work, so we have to go to a different means of describing the voltage and current in power systems. So we basically take the bottom peak here and flip it up so it has two positive peaks and take the average of that. That's referred to as root mean squared. And that gives us a number that we're going to talk a little bit more about as we get into this, okay? We'll talk about RMS, root mean squared. Another important aspect of voltage to know about is when there are transients on the signal, which happens when, in a power system or electronic systems. When there are transients, we refer to those peaks there as being referred to as asymmetrical peak. That asymmetrical peak is the highest voltage peak. Now, it might be there momentarily, but it has the potential to damage or puncture through insulation. Okay? A lightning strike is a transient activity that can create a very high momentary voltage spike that could damage equipment and break through insulation barriers. So we need to know what this peak voltage is. We refer to that as asymmetrical peak. And then when we design power systems or insulation on even small conductors, we have to have a certain level of insulation to handle the peaks. So we have an asymmetrical peak, and above that we have what's referred to as the basic insulation level, or BIL. So equipment that is rated for a certain BIL can withstand a certain asymmetrical peak, which is much higher than the peak value, which is even higher than the RMS value. So you pick which voltage term you want to use, but there's a reason for each one, and we're going to learn those as we go, okay? So this here has to do with the voltage peaks that we deal with in power systems. Okay, so when comparing AC and DC voltage and current, we have the RMS. And a very important part about RMS value is our major power lines that you see out in the streets when you're driving around, or in substations or at power plants, they're all rated in RMS. So when you hear of a 345,000 volt power line, that's RMS. If you hear of a 12 kV or a 500 kV, that's all RMS. When you're talking about our 120 volts outlet in our houses, that's RMS. Okay, so we are just used to the RMS. We have to sometimes convert those values to peak and peak to peak, or our asymmetrical peak and BILs, whatever. But the idea is our actual voltage that we're operating with is basically, on power systems, RMS. In simple DC circuits, it's not. It's not like that. We're using peak, or sometimes in DC it's considered a peak because it doesn't change. Okay, let's talk a little bit more about root mean squared. Root mean squared is a common term used in electric power systems mainly, where the voltage on these power lines that we're talking about that you see out in the streets and on freeways, what have you, in power plants, substations, it's all measured in RMS. So it's important to understand what RMS really is, okay? So as we do that, we're going to talk about RMS as being a fraction of peak. Peak voltage, as we saw on that slide, is the peak of the sine wave. And RMS is 0.707 times that peak. And 0.707 actually comes from 1 over the square root of 2, if you really want to get into it. But we're talking about 70% of the peak voltage is really the RMS voltage. And that's where we have a need to talk about RMS, because RMS in this equation here is for voltage, and it also applies for current. RMS current is 0.707 times the peak current. But we have a very important piece to understand here. The power associated with RMS values actually produces the same heating effect as DC. So when we want to equate RMS, we can equate RMS with DC. For example, if you take your toaster at home, it plugs into a 120 volt AC outlet. It's typically 1200 watts. Now, if we plug the toaster into the 120 volt RMS household socket, and let's say it toasts the toast in 1 minute, we can plug that same toaster into a DC battery bank and toast the toast in the same amount of time. So a 120 volt DC battery bank will toast the toast the same amount of time as it takes for a 120 volt RMS AC supply. Okay? The filaments, the toaster itself doesn't care if it's AC or DC, just like a light bulb filament doesn't care if it's AC or DC. Some devices do care, but simple resistive circuits like that and heating circuits, it doesn't really matter. But I wanted to point out the difference here with RMS versus peak. Okay? Now, when we're looking at it backwards, we can say that when it comes to voltage, 170 volts peak, okay, has an equivalent of 120 volts RMS. So if you consider what voltage it takes to give you 120 volts, it's roughly 170. If you use all the digits, 0.707, okay? Okay, now when we look at the graph of something like this, we have the peak voltage up on the top showing that we have 170 volts peak, okay? We have an RMS value, which is 120 volts. We have a frequency of, we're looking here, 2 cycles, and if we were to choose a frequency of 60 hertz, or 60 cycles per second, if there are 60 cycles in a second, each cycle is 16.67 milliseconds long. Okay? So that's the time it takes for 1 second, 16.67 milliseconds. And that's pretty short. It's pretty short. But what's really interesting is some of these very large circuit breakers used in bulk power systems can open up the circuit in roughly 2 to 3 cycles. So 40, 30 to 40 milliseconds, we can de-energize a complete high voltage transmission line. The equipment is that fast. It's protective relaying and everything associated with it. So timing is important, because when there's a problem out on a system, we want to be able to open up that problem and disconnect that problem right away. So when we talk about frequency and timing and RMS, we're getting the foundations for talking about the big bulk power system later. Okay, so that's what we have to deal with on AC, RMS, and that's what all of our power lines are based on, whether it's 12 kV distribution, 345 kV transmission, or even 765 kV transmission. That's all RMS. Okay? Now, when we apply RMS to our residential voltages, we have 120 volts AC RMS, means we have 165 to 170. If you use all the digits, it's 170, but 165 peak. If you talk about peak to peak, the peak positive to the peak negative, we're talking 330 volts. So what kind of voltage are we really dealing with here? Well, in power systems, our transmission lines are rated RMS like we talked about, and our household residential is RMS, but we might be talking about peak voltages when it comes to ground potential rise or lightning, or when it comes to faults on the system. We might be talking about peak events. We might, there might be some insulation levels, so we're talking about our BIL levels. So voltages have different terms for different reasons, and this basically explains those different terms. All right. Now, here's where it gets interesting. Here's where we're going to apply voltages to our bulk power system. Now, this chart is very informative. We're going to talk about a voltage class. These are just general voltage class numbers, and it has to do with the fact that manufacturers would like to manufacture 25,000 volt or 25 kV equipment, or 15 kV equipment, or 69, or 230 kV equipment. So that's kind of like a voltage class. Okay, then the voltage range, or the nominal voltages that actually fall in those classes, under 600 volts. 600 volts is like is customer service voltage, residential voltage, and this voltage would be our any of the outlets, our 100. Since everything's measured in kV here, we're talking 120 volts, which is 0.120 because it's kV. 120, 240, 208, 277, 480. Those are voltages that fall under that 600 volt class. We'll talk about all those later. That's considered low voltage. It's also considered secondary voltage. Then we get up into the power company side, and we're on the 601 to 7200 volts. Okay, that's called medium voltage. And we have power lines, some of the older distribution lines that were built, back in the early 1900s running at this voltage. Then we have 15 kV class, 12.5, 14.4 kV. Those are very popular. 12.5 kV is the most common distribution voltage in the country. Then we have 25 kV, which really runs around 24.9. And you go up. The 138 could be anywhere from 120 to 138 kV. These are what the power companies are actually operating. Our highest power system backbone voltage today is 765 kV. Now there are 765,000 volt power lines in the United States today. Okay, 230 starts to get into the EHV, or extra high voltage, and when you get above that, it's pretty much experimental. But we think of transmission and distribution, so we have secondary and distribution. Right here at 34.5, we have distribution or transmission because you can use it for either, and transmission. And generally speaking, distribution means that you can put equipment up on the lines to give customer service voltages. When you get into transmission, you're really not trying to give customers, service voltage from transmission. So we kind of divide. Distribution is more towards the consumption side. Transmission is more bulk power transfer side. So just to kind of help clarify that. Okay, now to summarize what we've covered in this module, okay, the first thing we did is we gave examples of the 4 fundamental terms used in power. That was voltage, potential energy, current is what flows, power, the rating of equipment, and energy, the rating over a period of time. And we talked about, the terms. We also talked about voltage with respect to DC, AC, RMS, peak, asymmetrical, BIL. We covered the different types of voltages that you're going to find in power systems. We also talked about the common voltages and classes of voltages in high voltage power systems, and we talked about secondary and distribution and transmission, etc.